Okay, so we're talking about energy, and we're talking about energy because we're talking about collisions, because you experience collisions all the time. Like, a good example would be I was making my way into town, driving my daughter to her basketball practice. You know how it goes. It was 5:30 a.m., and I saw a garbage truck on the intersection. And garbage truck ran the intersection, and so we smashed it. Okay, so we drove into a garbage truck. Garbage truck's fault, definitely. He claimed responsibility. He had to pay insurance, all that good stuff. But this giant garbage truck came down the hill on Brundage, just blew through that intersection. We smashed into it in our Tahoe because we were already going like 35 miles an hour. I saw the truck coming through the intersection, but I could not control that collision. So when you're thinking about collisions, even though I put the brakes on and all that good stuff, when you're thinking about collisions, think about the fact that most of you are driving now or very soon. So you need to be able to manipulate variables to control those collisions. So we need to think about energy. That garbage truck coming downhill and not stopping at the stop sign, not applying its brakes, transferring energy through the brakes by friction, had tons of kinetic energy carrying it through that intersection. My vehicle had a lot of kinetic energy. It's a pretty decent sized vehicle, or it was. And it was traveling at like 30 miles an hour. And so it had a lot of kinetic energy as well. So all this energy was going on, and we ended up in a collision. Crumple zone of the car absorbed some energy. Anyway, so you got to think about energy and collisions so that you can keep yourself safe. Well, if we're going to talk about energy, we got to go back to force a little bit. So when we think about force, force is a push or a pull. So when I pull on this Einstein doll, that's a force. When I push on the Einstein doll, that's a force. Gravity, you know, is the force that is pulling him down toward the center of the earth. Forces transfer energy. You know that according to Newton's second law, we can use that force equation, force equals mass times acceleration. But just like with velocity, you had to have a unit. Well, what the heck's the unit of force? Well, the unit of force, since it's a mass in kilograms times an acceleration in meters per second, the unit of force is what's called the Newton. So Sir Isaac Newton, of course it's named after, you know, he was just a beast. You think you're bored? Isaac Newton invented calculus during the plague. Do you know how bored you have to be to invent calculus? Anyway, so a Newton is equivalent to 1 kilogram times 1 meter per second per second. That doesn't mean anything to you because you have no frame of reference. What the heck's a Newton? So, of course, here I am in my science room. I have my handy dandy 1 Newton, not Wayne Newton, no. 1 Newton. So I have my little 1 Newton here. I can feel this, and I can feel what 1 Newton feels like. Well, you don't have 1 Newton at your house. You're home during quarantine. Do you have a Snickers bar? So a Newton feels like what 100 grams feel like. So if I take a Snickers bar, and I know I've been keeping these away from my children. All right, so somewhere it says the mass on it. Oh, duh. All right, so we look at how many grams a Snickers bar is. 52.7. So Snickers bar, 52.7 grams. I'm gonna round that off to like 50. So if I take 2 Snickers bars and I put them in my hand like this gives me a feeling for what 1 Newton of force feels like. Do you think this feels like very much? No, it's really easy. I can accelerate these really easily. So 1 Newton of force is what it feels like when you have 2 Snickers. You don't have Snickers bars. You would have already eaten them. Do you have a stick of butter? If you happen to have a stick of butter in your house, stick of butter has a mass of like 113 grams. It's close. We can call it 100. You could lick it a few times first if you want to. Put a stick of butter or margarine in your hand. I wonder if they're the same mass, actually. This is what 1 Newton feels like. Not very much. So a Newton of force is not very much force. All right, so you have a handle on what a Newton feels like. Now, when we think about, I'm going to need those Snickers bars back. When we think about energy, the ability to do work or cause change, you know there's 2 kinds, kinetic energy and potential energy. I'm focusing on gravitational potential energy, but of course there's elastic potential energy. When we want to calculate energy, we can use for kinetic energy, Ke equals 1/2 mv squared, or for gravitational potential energy, mass times the acceleration due to gravity times whatever height you are. So regardless, you end up with a mass and basically an acceleration as your unit. Well, we use units called joules. A joule, named after James Prescott Joule, he didn't invent calculus, is equal to a Newton meter. Let me find my candy bars. Could get interesting. I got one. I don't honestly know where the other one went, and I'm gonna get in trouble with my offspring because they're each supposed to get one. Anyway, I'll use my butter because my butter is the equivalent of a Newton. If I take my stick of butter, here's my handy dandy meter stick, oh science. If I use my stick of butter, if I lift, way to go, McCullough, you're playing this one out well. If I lift my stick of butter up from Earth the distance of 1 meter, that just used 1 joule of energy. And I'm not like, oh my gosh, so exhausted now. A joule is not that much energy. That's why we normally talk about kilojoules. So a joule is the energy I had to expend to lift this stick of butter 1 meter on the surface of Earth, considering Earth's gravity. So that gives you a little idea for what a Newton feels like, that unit of force. Gravity's pulling down with 1 Newton of force on this right now. Or sorry, the force that I feel due to the gravity of Earth, which is 9.8 meters per second every second, is 1 Newton of force on this stick of butter. And a joule is the energy I need to put in to raise the stick of butter 1 meter, to raise 1 Newton 1 meter. So joules a Newton meter. A Newton is a kilogram meter per second per second. Just think of it as a stick of butter in your hand and you should be okay. So let's learn more from Professor.
Hey, it's Professor Dave. I want to tell you about kinetic and potential energy.
He knows a lot about the science stuff. Professor Dave explains.
We now understand a more rigorous scientific definition of the word energy as being the capacity to do work. But as we said, there are a few different kinds of energy, so we must talk about all of these varieties. First, we will discuss kinetic energy and potential energy. Kinetic energy is the energy an object possesses by virtue of its motion. If we recall Newton's second law, we know that the application of some net force will move an object with some mass at some constant acceleration. We also know that work is equal to force times distance. Note the presence of mass in the kinetic energy expression. This means that if two objects with different masses are moving at the same velocity, the more massive object will necessarily have more kinetic energy. Now let's discuss potential energy, which is forever intertwined with kinetic energy. Potential energy is the energy an object possesses by virtue of its position in a field, whether that is a gravitational field, an electromagnetic field, or any other type of field. If you lift a ball up into the air, you are increasing its gravitational potential energy as it moves farther away from the ground. If you release the ball, that potential energy is converted into the kinetic energy of motion as it falls. The closer an object is to the center of gravity of the Earth, the less potential energy it has, and as you pull it up and away from the ground, it gains potential energy because it has an increasing potential to fall some distance to the ground. It may seem strange to bestow an object with more energy just by lifting it into the air, but remember that we have to eliminate our prior conceptions of the word energy in favor of more rigorous definitions. The potential energy of a compressed spring or an arrow ready to be released from a bow is where the kinetic energy of motion comes from. It is like a kind of stored energy. In this course, we will frequently be discussing gravitational potential energy for objects on Earth, and for any object this will be equal to the mass of the object in kilograms times the free fall acceleration due to gravity for the Earth times the height of the object in meters. The greater the height, the greater the potential energy, as this represents the work that can be done by gravity to produce the motion of a falling object. There is also elastic potential energy, such as with the spring or the bow and arrow, and we will discuss this later as well. For now, we just need to understand kinetic energy as the energy of motion and potential energy as the energy of location.